So let's do a quick review of last lecture. So last time we kind of did a high-level taxonomy of radar. And it looks very similar to sonar. So in terms of the waveforms that radars use, we said that there's two main types. You either have pulse radar, which sends these short pulses, or you have a CW or a continuous wave radar, which is continuously transmitting. And specifically, there's two types of continuous waveforms that are commonly used in radar. So we have FMCW radar, which stands for frequency modulated continuous wave radar, and that's the one that sends these linear frequency chirps. And then you can have your PMCW radar, which stands for phase modulated continuous wave radar, which sends basically ranging codes such as PN sequences or M sequences, exactly like GPS. We haven't talked much about PMCW yet, but we'll get to it today. And then in terms of the antenna configuration, you can have systems that just have one transmit and one receive antenna, and that's a single input, single output, or a SISO system. Or you can have, as it's called, diversity in your antennas, multiple transmitters, multiple receivers, and then that makes a MIMO system. You can, of course, have like in-betweens, like a SIMO system, which has one transmit, multiple receivers, or a MISO system, which has multiple transmitters, single receiver. But I mean, that in my mind, all of those fall under MIMO. If your transmits or receives or both are more than one antenna, I would like to just call it a MIMO system, just to simplify it. Okay, and then we basically developed a very detailed signal model for FMCW radar. And for now, we are assuming SISO. Although everything we say for range and velocity estimation, exactly as is, will apply to MIMO systems. But for now, just to keep our signal model a little simpler and more tractable, we are starting with a SISO system. We will get to MIMO very soon. So before we look at the signal model, just remember that the most common type of radar that is used for autonomous robotics today is MIMO FMCW. Okay, that's like 99% of what's out there for this application. Okay, for other applications, you can have other things. PMCW, it's very interesting. I'll talk more about it. I'm personally very much in favor of seeing more PMCW systems developed and deployed. But right now, for very practical reasons, it hasn't been widely used and deployed, and we'll talk about it more. Okay, so let's look at our signal model for FMCW. So we said that after down conversion, so after basically you mix your received echo with the transmitted chirp, you get this IF signal, which is given by this expression here. So let's break it down. So there's a mu that's mu and alpha are just constants. Okay, so you can completely ignore them basically for the purpose of DSP, but this is for completeness included here. Mu is the gain of your low noise amplifier on the receiver front end. Alpha is the attenuation from the round trip wave propagation and also the RF reflectivity of your target. So all of that is lumped into just one complex factor alpha. And then you have basically a time varying term with frequency delta f, e to the j 2 pi delta f t. So that's the frequency of the IF signal delta f. And then you have a phase term, which doesn't change over time, but it depends on the round trip delay tau. So we just call that e to the j phi of tau. So this is our phase term, essentially, and that's our frequency. Or time varying term. Okay, so what is specifically delta f? We showed that there's basically two things contributing to the frequency of the IF signal. There's a f sub t, which is proportional to range. Okay, so ft is just your slew rate times the round trip delay, or time of flight tau, which becomes equal to 2 times the slew rate times the target range divided by the speed of flight. Okay, so that's the first term. But there's also a contribution from the Doppler effect. So the frequency is actually Doppler shifted by f sub d, which is our Doppler frequency. And specifically, f sub d is proportional to the relative radial velocity between the radar and the target. Via this expression, it's minus 2 times the time derivative of range, and the time derivative is that relative radial velocity, times the carrier frequency over c. Or you can just write r dot as v sub r to make it more clear that that's a radial velocity. So your ft is minus 2 vr fc over c. Okay, and this is we said it's a complication when it comes to how do we process this IF signal to do range and velocity estimation, because it couples range and velocity. And if we can only measure a delta f, then how do we break it down to like what was range, what was velocity? It's a big complication. It turned out that for most robotic application, this is actually of very little consequence. Why? Because this Doppler shift term turns out to be much smaller than ft, which is range dependent. And for practical purposes, in most robotic applications, you can just ignore this term. Okay, and then your delta f becomes equal to ft, which is just basically a function of range. Okay, so we checked with some numbers that are actually kind of pretty conservative estimates. So we assume a target going at 100 miles per hour. That was just a few meters in front of the receiver, and receiver working at 77 gigahertz. Even for that case, we showed that your ft is less than 1%. Or f Doppler is less than 1% of ft, so that's why we can ignore it. But this is one of those cases that it's extremely important to remember these assumptions that go into our algorithms and the DSP, because you might be working on some different application. Say you're working on a military radar that is supposed to track missiles. And missiles can go, I don't know, 10 or 100 times faster than this maybe. And then this assumption breaks down. And then if you use your vanilla DSP, of course, it is not going to work. So extremely important to remember these. And every application you're working on, just check your parameters against these assumptions and make sure they're valid. For what I call everyday robotics, this is fine, right? I mean, we don't work with things that go faster than 100 miles per hour. Even in like autonomous driving, that's a very conservative assumption usually. Okay, so that's that. And then this phi ft, the phase term, it's given by this expression, 2 pi times carrier frequency minus b tau over 2 times tau. We'll get back to this today. For now, it's just a phase term because we're working on how do we do ranging, how do we do range estimation. When it comes to Doppler, we'll start looking at this. Actually, we'll do that today. Okay, any questions about the signal model here? Okay, so let's continue. And then we said that in the more general case, if you have more than one target, the exact same signal model basically applies. If you have k targets, you just sum up the IF signals that you're receiving from each of them. Okay, so it just becomes this sum. So each has its own attenuation alpha I, and each has its own frequency delta fi, and its own phase term phi of tau I. Okay, you just sum over all targets. So here's just one simple, visual example. You have an antenna with a very wide radiation pattern or gain pattern, so it's almost isotropic. And then the chirp that you send, in this case, it has hit 3 targets simultaneously at ranges R1, R2, and R3, and then you receive all 3 echoes almost at the same time. So if you look at basically this plot here, it kind of shows what you're receiving. So the green is the frequency versus time for the transmitted chirp, and then you receive 3 chirps back, each with a different delay, so call them tau 1, tau 2, and tau 3, and each of them basically induces a frequency in your IF signal that is proportional to the range of that target. So you get a delta F1, a delta F2, and a delta F3, right? So this naturally just extends to a case with multiple targets. So now we are ready to do a range estimation, right? Because we know that these delta Fs are proportional to range, right? It's just equal to 2, let me make sure I get it right from the board, 2 times the slew rate times the range of ith target divided by the speed of light. That's what the delta Fs are. So again, exactly like the case of CTFM sonar, now we have converted by using these chirps a range or a time of flight estimation problem to a frequency estimation problem. Now we need to estimate the frequency of this IF signal. Again, as I said multiple times, there's tons of different algorithms that work when it comes to a spectral estimation or frequency estimation. The simplest one is our good old Fourier transform, right? You just take a Fourier transform and you're expecting to see peaks at these delta F frequencies. And that's exactly what happens. So if you just take your IF signal, and remember, this is the IF signal from one chirp, right? So you have down-converted one chirp. You've down-converted that. That's the SIF that you get. And the ADC has sampled it, so you get n points or n samples in it. So n samples corresponding to one down-converted chirp. Then you do an n-point FFT on it. And here I'm kind of loosely using the term FFT. I mean, we all know FFT is the actual algorithm, the implementation of a discrete Fourier transform. So to be mathematically correct, I should really call this DFT, the discrete Fourier transform. But I mean, just for convenience, we are all, you know, when you program, you just write FFT. I mean, technically, FFTs are designed and they're most efficient when n is a power of 2. But I mean, you can extend it and it will work for any n. Okay, so just a quick note. Throughout the rest of the course, I'm going to just constantly say FFT. But I mean, mathematically speaking, to be mathematically correct, that's a discrete Fourier transform. FFT is just the algorithm that is used to calculate the discrete Fourier transform for you. There's other algorithms. You could use something like the chirp Z transform or other things. But again, the point is you take a discrete Fourier transform. And so you get this, what we call the SIF of k. Now k is the index of your Fourier transform. And what you need to do is just look at the absolute value of f, or the magnitude of f, and find the peaks. And those peaks would give you the delta f, your estimates of your delta f. So, for example, in the case of what I showed you in the previous slide, where we had 3 targets, if you do that, we'll see 3 peaks in the FFT at indices k hat 1, k hat 2, and k hat 3. And then to actually find the range of the targets, you first convert the indices to frequencies, right? So the indices go from 0 to n minus 1 because you are doing an n-point FFT here. To find the frequencies, you just do your index divided by n, which is the total number of points in the FFT, times the sampling rate, f sub s. F sub s is your ADC sampling rate. So that converts your index k to your delta f frequency, and then from delta f to range, that's another scaling, right, which we just looked at. So to find the range of the ith target, you do delta f times the speed of light divided by 2 times the slew rate. And the slew rate, remember, is known because we know what chirps we are sending. B is known. It's actually a configurable parameter. Usually you can set what slew rate you want at your transmitter. So this is it. Basically, that's k is the index where you see the peak in the FFT times the sampling rate of the ADC times the speed of light divided by 2 times the number of points in your down-converted signal times the slew rate. That gives you range in meters. And you're done, right? So that's how you do ranging. That's our algorithm. It's just a Fourier transform. It's an unbiased estimator. It's very efficient and easy to implement, and it's widely used. Yes? Yes, good question. What do I mean by unbiased? So by unbiased estimator, I mean that I'm going to explain it a little loosely because unbiased in like statistics, I mean, there's like, I don't want to go through the full math, but loosely speaking, it means that if I run this algorithm many, many times, okay, and I average all those R hats that I estimate, the average is equal to the true ground truth underlying R. There is no systematic error in my measurement. As opposed to, if you remember, in the case where we were talking about sonar with a simple thresholding detector, that was a bias estimator because there was always, the measurement would never be equal to the underlying ground truth. There would always be, some systematic error in it. So unbiased means no systematic error. There's still noise in your estimate, but the average of the noise is 0, or the average of the error that you make in your estimate is 0. That's what we mean by unbiased. Okay, so that's how we do ranging. Okay, now what is from this algorithm, what is the range resolution and what is the maximum range that we can get? Exactly like the case of sonar, the resolution is determined by basically the width of the FFT bins, right? So the minimum frequency you can discriminate is 1 FFT bin. Like I can go from K to K plus 1, and that's the minimum frequency discrimination you can do. And so that determines our range resolution. And maximum range is determined by the maximum frequency we can estimate, which is basically tied to the sampling rate of the ADC. So if the peaks is at basically n-1, that's the maximum frequency you can distinguish, and that determines the maximum range. So mathematically, what we get is minimum range discrimination corresponds to 1 FFT bin. So what is the frequency for 1 FFT bin? That's just your sampling rate, Fs, divided by the total number of points in your FFT, which is also equal to 1 over t, where t is, remember, the chirp duration in seconds, because you have this relationship between the number of samples, the chirp duration, and the sampling rate. Okay, so with that delta F minimum, what is the minimum range that you can discriminate? You can just plug that delta F min into our range equation. So delta R minimum, which is our range resolution, becomes delta F minimum times speed of light divided by 2b. And you plug this into here from the top, and then your delta R min becomes c over 2b times t, or speed of light divided by 2 times the bandwidth of the chirp, right? And remember, the bandwidth of the chirp is, if you look at this frequency versus time, the bandwidth of the chirp is, if you go from fc to fc plus slew rate times t, where t is the total chirp duration, this is our chirp bandwidth b, which is slew rate times the total duration. This is exactly the same expression, by the way, we got for CTFM sonar. No changes because it's, same principle of operation, same algorithm, so it makes sense that you get the same basically type of performance out of it. What about the maximum range? Maximum range is, again, the maximum frequency you can find in your FFT times the speed of light divided by 2b. What is the maximum frequency? Well, we're searching. We know that range is always positive by definition. So when we look at our FFT, our delta F can be from 0 to a maximum, which is the sampling rate, Fs. And this is from the Nyquist, basically, theorem. So we plug in basically our delta F max is the sampling rate, plug that in, and that is the maximum range, which is sampling rate times the speed of light divided by 2b. Okay, so here immediately we see one of those basically trade-offs between your range resolution and the maximum range that you can discriminate. Why? Because let's say you keep every parameter the same, and we are just varying the slew rate. Okay, so if you increase the slew rate b, what happens to delta R? Delta R, if you increase b, it likes it, right? Because delta R becomes smaller, that means you get better range resolution. So it's good for delta R. Delta R goes up, or it goes down, actually, which is desirable. But also, the maximum range goes down, which is undesirable. So it will increase your range resolution, but decrease the maximum range. Okay, so that's a very important, trade-off. If you're in charge of, designing or using a radar for some application, one of the design parameters you need to choose, if it's a FMCW radar, is going to be this slew rate. And then you have to look at your application, decide what is the maximum range you need to see, what is the range resolution that is required, and then based on those, decide what is the optimal B to use. And it's a trade-off, so somebody needs to, give something. You cannot, have the best possible resolution and the best possible maximum range. There's always this trade-off between the two. Okay, yes?
For like radars that work at these frequencies, like, do they ever do real sampling, or is it usually always IQ?
Great question. So the question is, the radars that operate, we're talking about at these frequencies, when it comes to the ADC sampling, do they do real samples or IQ samples? For FMCW, it's always IQ samples because we need to have the full complex signal, as we'll see in a second, especially to do Doppler frequency estimation. That phase term needs to be known. Basically, we need to have this e to the j phi of t, and as we know, the only way you can find the phase is to have the full complex signal, or both the I and the Q component. So it's always full IQ. Yeah. Physically, you get out of your ADC. You can't, in circuits, you can't have, complex signals. So it gives you two data streams, one for I, one for Q, as you know. And then in DSP, you mix them and make a complex signal out of it. Okay, so other questions? All right, let's continue. So now we want to talk about velocity estimation. We know how to do range, right? And next is velocity. And velocity here, it's basically the velocity from the Doppler shift, which, as we know, it's the relative radial velocity, okay? So it's that VR that we are going to see how to estimate. So it's not going to give us the full, velocity vector of the target. It will only give us the component that's projected to the radial direction. Still extremely useful, right? But that's an important thing to know, that the velocity that you get is just a radial velocity. Okay, as I told you, that's where this phase term phi of tau becomes very important, because this does contain Doppler information in it. Now, to see how velocity estimation works, first let's look at a very simple example. Just two chirps sent consecutively from the transmitter, and they are echoed back from the same target. Okay, so two chirps here shown in green, and then you get two echoes in blue from the target. And let's say your round trip delay from the target was, from the first chirp you get tau 1, from the second chirp you get tau 2. Why did it change? Because we're assuming the target has some velocity. Because it has some radial velocity between the two chirps, it moves slightly, and that slight movement can affect your round trip delay or time of flight tau. Okay, so target has some radial velocity v sub r relative to the antenna, and here we are assuming that basically within this small time t that has passed between the two chirps. So this first chirp was sent at time 0. The second is sent at time big T. And because this big T is typically very small, so these are on the orders of like tens of microseconds, basically, for the types of radars that we're talking about, or sometimes even less than 10 microseconds. Because it's such a small time elapsed between the two consecutive chirps, well, the target does move if it has this radial velocity, but it doesn't move enough for that change in the basically in the target range to affect the IF frequency delta f. Okay, so again, the assumption here is that Doppler term does not affect delta f, which is exactly the same assumption we talked about a few minutes ago. So delta f is the same between the two consecutive chirps, but nevertheless, the round trip delay is changing a little bit, and that would affect our phi, because phi is only a function of tau. How much does it affect phi? So let's look at it. So as you know, phi. So let's first look at the phi 1, which is the phase of the downconverted signal from the first chirp. Okay, so you have like SIF 1 of t from here, and you get a SIF 2 of t from this one. So what is phi 1? The expression for it was 2 pi fc minus b tau over 2 over tau. Okay? But if you look at the numbers, b times tau is always, again, for the applications we work with, is much, much less than the carrier frequency fc. Like b tau is typically a few megahertz. Carrier frequency, as you know, it's like 24 gigahertz or 77 gigahertz. So your b times tau is like 1,000 to 10,000 times smaller than fc. So inside here, you can assume this is almost 0 in comparison to fc, and then your phi just becomes 2 pi times the carrier frequency times tau 1. Just like that, what is the phase of the second IF signal? That becomes 2 pi fc tau 2, right? So the phases are directly proportional to the taus. Okay, so now let's look at the phase difference between these two IF signals. So I'm going to subtract the phase of the second IF signal from the phase of the first IF signal and see how much between the two chirps the phase of the signal we receive has changed. So that delta phi, phi 2 minus phi 1, let's plug in. So it becomes 2 pi delta times carrier frequency times delta tau. And what is delta tau? That's just delta range divided by c. That's by definition, times 2, right? So that's why you get a 4 here. So remember, tau is 2r over c. So your delta tau becomes 2 delta r over c. And that's what we've plugged in here. You can write it like this. 2 pi t times 2 fc delta r divided by c times t, where t is the chirp duration in seconds. But here's something interesting. This delta r over t, that's how much the range changed over t seconds. So that's the radial velocity of your target, or the relative radial velocity between the target and the radar. So that's vr, or almost equal to vr. If t is small, which we know is. And then this term here, 2 fcvr over c, that's our basically Doppler shift by definition. So you see that this delta phi between the two consecutive chirps, that the phase difference is proportional, in fact, to the Doppler shift. Okay? So now that that's the case, that means if we estimate or calculate the phase difference between two consecutive chirps, we can then estimate Doppler shift from that, right? So from this expression, then you just basically invert that, and you get your estimate of the Doppler shift is just delta phi divided by 2 pi t. Again, t is the chirp duration, okay? And from the Doppler shift, we can find the relative radial velocity between the target and the radar, which, as we know, is just minus fd times lambda over 2. Lambda is the wavelength. In terms of the phi, it's this expression, okay? So that is, in principle, how you can estimate velocity in a FMCW radar. Yes?
If you were saying like the radial velocity, if we have a MIMO array, then how to say like what is the radial velocity with respect to each antenna?
That's a great question. So the question is, we're talking about radial velocity. But what if we have a MIMO array, then with respect to this radial is with respect to which antenna? So if I were to draw it, if I have like multiple antennas, right, and then there is a target, when we talk about radial velocity, is it radial with respect to this? Is it radial with respect to this? Is it radial with respect to that, right? That was the question. Well, that's a very valid question, but this is only, I think this picture is kind of like, exaggerated in the sense that the target is like so close to the antenna plane that the ranges are actually different. When we are talking about, far field targets, the target is actually like way out here. So we assume that range is, the same to all of, like the antennas are so close to each other relative to how far the target is, that the range is the same to all of the antennas. And that's a good assumption. I mean, usually your antenna aperture is like a couple of inches by a couple of inches, and then if your target is like 20, 30 meters away, or even 10, 5 meters away, you can assume the range is almost the same respect to, all of the antennas. But again, that's a great question, because that's one of the assumptions that in some applications might not be valid. Like if your target is like too close, then yes, you can pick up different Dopplers on different antennas because of exactly what you brought up. But for us, we assume that, yeah, its target is far away. The range is almost the same with respect to all the antennas, and the antennas are really close to each other.
But if the target is very close, then can we just estimate the tangential velocity?
Yes, you can. It becomes complicated, but, well, not like complicated to the point that you cannot do it, but you can absolutely do that. Then you need to, find Doppler with respect to every antenna, and then by comparing those Dopplers, then you can also find tangential velocity, I'm sure. I haven't seen anybody do it. Makes for an interesting research problem, I guess, but it's doable. Okay, so that's how we find Doppler from just 2 consecutive chirps. And there is a limit to what velocity you can find. Why is there a limit? Because note that it's based on that phase shift between 2 consecutive chirps. And if the phase shift is bigger than pi or smaller than minus pi, it wraps around the circle and then basically becomes ambiguous, right? So this is valid as long as your delta phi is less than pi, bigger than minus pi, okay? That's important. So that limits what is the maximum velocity you can unambiguously detect. So what is the maximum velocity, or the absolute value of the maximum velocity you can unambiguously detect? That is proportional to the maximum phase you can unambiguously detect, which is pi. So you plug in pi into this expression for delta phi, and then the pi and the numerator denominator cancel out, and you get lambda over 4t, which is the maximum velocity. So the radial velocity you can estimate is between lambda over 4t and minus lambda over 4t. That's the limit. And again, if you need to increase that limit on what velocity you can detect, one thing you can do is, well, either you can go to higher frequencies, lambdas. So that's one reason like 77 gigahertz is better than 24, one of the many reasons. Or you can reduce t. So send shorter chirps, basically, and that helps with your unambiguous velocity. Okay, so this is fine. This is one way you can estimate velocity. But just looking at 2 consecutive chirps, it's not a very robust algorithm. Because remember, like in reality, these signals are distorted, they're noisy. So if you just look at 2 chirps and compare the phase of the 2, you get a really, really noisy estimate of that phase difference, which becomes a very noisy estimate of your Doppler shift and ultimately velocity. To robustify this idea, what you can do is basically extend it, and instead of just looking at 2 chirps, look at a whole bunch of them. Look at tens or hundreds, right? But the core idea is exactly the same. So what is done in practice to robustify this velocity estimation algorithm is that you define what is called a frame, okay? And the frame is basically a collection of m chirps that are sent consecutively. Remember that your transmitter is just constantly, it's a CW system, right? It's just constantly sending these chirps forever, right? On the receiver, so in DSP, you can define a frame, and it's up to you, like how long you take your frame to be. But you just collect a bunch of IF signals, m of them, right? Chirp 0 to chirp m, and you decide what is a good choice for m. Typically, it's like a few tens to a couple hundred or something like that. So I've seen like numbers between 32 to 512 or so. But you choose some m, and then that makes up for a frame of data. And then instead of looking at just 2 consecutive chirps, you look at all of them and then estimate your Doppler. But the core idea is exactly the same. So what happens, and here our notation is going to get slightly more complex, so let's make sure things make sense. So I'm calling now SIF, I'm assigning 2 indices to the IF signals, a m and an n. So SIF of m and n. M is the chirp index. Okay, so that means this SIF is coming from which of the m chirps inside the frame. So little m goes from 0 to m minus 1. And little n is the ADC sample index, just like we had before. So little n goes from, those are the samples you get out of your ADC. So that goes from 0 to big N minus 1 because we're sampling each chirp n times. Okay? So that's our notation, just to make sure it's clear. So now, if you look at the phases of these SIF of m and n, the first one, SIF 0, for m equals 0, let's call that phase of that guy just phi 0. That's our reference phase. That's like this, the phase at the start of the frame. Okay, we just call that phi 0. It's equal to 2 pi fc tau 0. Okay, that's our reference. But then every chirp that comes after that in the frame, it has a phase phi m, which is phi 0, plus m times the delta phi. Delta phi is that phase difference we just calculated between two consecutive chirps. So the chirp that comes after m chirps, it just has a phase difference of m times delta phi with respect to the first one, right? And what is the assumption that goes into here? We're assuming that the radial velocity is constant within one frame. And because of that, the delta phi of every two consecutive chirps becomes constant. And we know what delta phi was, right? Delta phi was just minus 2 pi times Doppler frequency times t. So the phase of the IF signal number m becomes phi 0 minus 2 pi f Doppler times m, which is the chirp index, times t, which is the chirp duration. Okay? So what is the total time of one frame? It consists of m chirps, and each chirp has a time of t. So a frame time tf is equal to m times t, which is the chirp time. Okay? All right. So what is our new signal model for one full frame? So SIF of m and n. There's nothing new here. So it's equal to mu times alpha. So mu alpha is again the gain and the attenuation factor. This is our good old frequency term that we had, e to the j2 pi delta f times nts. I'm writing the discrete version here, so that's why you get n times ts. Ts is the sampling interval of the ADC, and n, remember, is the ADC index. Okay? So that's, and delta f is the term that is proportional to range. And then you get e to the j phi 0, so that's the starting phase of the first chirp. And then this e to the minus j2 pi f Doppler mt, that is basically coming from here, which was phi 0 plus m delta phi. So again, this expression here is exactly what we had here. Same signal model, right? We have just expanded what phi would be for chirps that are inside a frame. That's all we had done. There's no new physics, no new, exactly. There's no new physics here. We've just expanded the math to include, to be able to talk about frames instead of individual chirps. So again, when you see expressions like this, I mean, at first glance, they look kind of, too much to digest. But always, take a deep breath and go term by term and make sure everything makes sense. Again, let's do it together one more time. Mu is the gain. Alpha is attenuation. This is our good old e to the j2 pi delta ft. We have just discretized it through the ADC. This e to the j phi 0 is the starting phase at the very beginning of the frame. And then this is just e to the j 2 pi. And this here is like m delta phi. That's what it is, e to the j. Now, what's really interesting here is now we have this complex exponential term, which is proportional, the frequency of it is the Doppler shift, and it's sampled at a different sampling rate. It's sampled at, every t seconds, which is a chirp time. So here we have a different sampling rate for delta f. Delta f is sampled at ts, which is our ADC sampling time, and that's fast. That's why this is called fast time. And then our Doppler is sampled slowly because it's sampled between chirps, and that's every t seconds. And this is usually called slow time in the context of radar. So how do we process this? Processing turns out to be extremely easy. Before we do that, you can even make it more general if you have k targets. what happens? You just sum k of these, one for each target that is echoing back to you. So it's the exact same expression. Mu is mu because it's the same gain for all targets, but then now every target going from 1 to k has its own attenuation factor, its own delta f, which is proportional to the range of the ith target. It contributes a phi 0 to the starting phase of the frame, and it has this term, which is the phase of the IF signal, and it has it's proportional to the Doppler frequency, which, as we know, gives us VRI, which is the relative radial velocity of the ith target. Okay, so that's the general signal model. And here, two assumptions go into the signal model. So we have assumed that within one frame, both the target range and the target velocity or radial velocity of the target are almost constant. Okay, so the frame should be long enough, should be short enough that both these assumptions are valid. R doesn't change too much for each target, and VR doesn't change too much. So that means the frame should be short enough. But it also should be long enough such that it gives us enough chirps so that we can estimate Doppler accurately. What are some typical numbers for reasonable frame times for applications we're interested in? No more than 100 milliseconds, I would say. If it goes above 100 milliseconds, except if things are moving really, really slowly, that's where I would start to worry, like, are these assumptions still valid or not? And 100 milliseconds frame time, that's like a 10 frames a second radar, so it's something, very interesting. Of course, if you can work with shorter frames, it's better because that means these assumptions are even more valid. But if things start to become too long in your frame, or if the frame duration starts to become too long, you should plug in some numbers for typical range, typical velocity that you get, and see, okay, are the assumptions still valid or not? That went into the signal model. Okay, how do we process this? Processing is a two-step thing. First step is the same as we did before. So first you do range estimation, which is just an endpoint FFT, okay? But now your signal is a function of two indices. You have N and you have M, right? So your first FFT is along the N axis, and that is called the range FFT, or range processing. Range processing. So when you do range processing, you basically just take the FFT of this IF signal over N. Okay, and that's a big endpoint FFT. So everything that doesn't depend on N, you can just take them out of the FFT sum or integral. So mu is mu, alpha I is alpha I. This stuff is also, you can take them out because they are not functions of N. The only term that has N dependence is this, e to the j 2 pi delta fi nts, which is the same thing we had before when we did our ranging. So you take the FFT of that, call that FFT, I'm calling it R tilde I of k. Okay. In fact, I'm also, in this R tilde I, I'm also including the constants. So the alpha I, the mu, and the e to the j phi I 0, I'm also lumping those into Ri, just to simplify the math, right? So Ri is our range FFT, and we know from what we just discussed that for each target, if you look at the magnitude of R tilde I, it will have a peak at an index that is proportional to the range of that target. In fact, it will show a peak at an index k hat I, which is equal to n times delta f hat I over fs, and delta f hat I is proportional to Ri, or R hat I, which is the range of the ith target. Okay, so range processing converts your raw IF signal into something that shows peaks in indices proportional to the range of the targets. Now look at this. We have something very interesting. As a function of M, what we have here is just this complex exponential, right? It's like a complex exponential with a frequency that is the Doppler frequency of the ith target, FDI. So if we take now an FFT over M, that should give us peaks that are proportional to the Doppler frequencies, right? So again, now our Doppler estimation or velocity estimation became a spectral estimation or a frequency estimation problem. We need to estimate these FDIs. Simplest algorithm is a Fourier transform. So let's do that. So now you do a second one-dimensional m-point FFT along the m-axis. This is called Doppler FFT or Doppler processing. So now we take the FFT over m of the already FFT'd or pre-processed IF signal, and this time you can take the R tilde out of the FFT because that does not depend on m, so you just FFT this complex exponential term, and let's call that d tilde I of L. Okay? So d tilde I of L, it will show peaks at indices L that are proportional to the Doppler shifts or Doppler frequencies of individual targets. Very specifically, for the ith target, if you look at the magnitude of d tilde I, it will show a peak at L hat i's, and the Doppler shifts are just L hat over m, which is the number of points in the FFT, times this F prime S. What is F prime S? Is the sampling rate in the Doppler axis, okay? And the Doppler axis, we said we are slow time, so we're sampling at 1 over t rate. So F prime S, which is 1 over t, is the effective sampling rate along the Doppler axis. And it basically becomes minus L hat I over TF. So that's the estimate of the Doppler shift of the ith target. And Doppler shift, we can also easily convert that to radial velocities. Radial velocities are Doppler minus Doppler times lambda over 2. If you plug everything in terms of the indices at which you see the peaks along the Doppler axis, if you multiply them by lambda, divide by 2 times the frame time, that gives you the radial velocities of the targets in meters per second. I know the math becomes, a bit dense here, so this is the kind of a thing you have to, sit down and go through it at your own pace and make sure every step makes sense. But I very intentionally, left nothing out when it comes to writing down the math and, clarifying all the assumptions, because I think it's important to get comfortable to work, at this level of mathematical complexity. Again, the point here is that, even like lots of textbooks, when it comes to DSP, they just tell you, oh, range and Doppler processes are just 2 FFTs, go do it and you're done. And of course, well, yes and no, right? I mean, yes, in, again, 95% of the cases, but there's a lot of assumptions that go into this. And it's important, I think, really, really important for you to know where those assumptions were made, what are the assumptions, and at the end of the day, why FFT? FFT is just, or Fourier transform is just a convenient algorithm that lets us find these frequencies we are looking for. There is nothing, sacred about FFT. You could do another, many different, algorithms exist that can be used for spectral estimation. So FFT, again, it's standard because it's efficient and easy and convenient to use, but you can actually, in terms of performance, beat FFT by a long margin if you use, more sophisticated algorithms. So let's look at this graphically. Hopefully this next slide kind of, instead of, the math gets really dense, but this is visually really, at the end of the day, what happens. It's a very, very simple process to do range and Doppler estimation. So the way to read this, it's like 4 blocks. So you start here, so that's number 1. You go from 1 to 2, 2 to 3, 3 to 4. Okay, so let's go together. One is there's nothing happening in one. So there's just from your ADC signals coming in, raw signal, okay? So you take one frame of data and you just populate it in an m by n matrix. So you have in rows are your index n, which is ADC samples, and columns are the chirp index. So you put your first IF signal from the first chirp in the first row, SIF0n. The second IF goes in the second row, third one goes in the third row, and so on, all the way to the mth one. Okay? So that's just, ordering your data before you process it. Now you want to do range and Doppler processing. To do range processing, you FFT each row. Every row of the matrix, just do a big n point FFT on it, and that converts basically ADC samples to the range index k. And we call that R tilde, right? So you get R tilde k, R tilde k, R tilde k on the rows, but each row is multiplied by a different complex exponential that is proportional to the Doppler shift. So you get, first one is multiplied by just e to the j0, second one e to the j 2 pi fdt, third one e to the j 2 pi ft 2t, and so on and so forth. Okay, so that's your range processing. Doppler processing, now you take FFTs of every column, right? So FFT every column, this is going to be an M-point FFT because you have M points. And again, remember, every cell here is one ADC sample. One ADC sample. So it's just one number, one complex number in every cell, right? So that's our data matrix, basically. So you FFT the columns, and then that converts your chirp index to a Doppler shift index, L, right? And that's why we call that, after the FFT, we call it d tilde of L. So now if you look at your cell, basically KL, that gives you what we call SIF, big SIF of K and L. And then the K is proportional to the, basically to the range, and L, so K is range index, and L is Doppler index or velocity index. How do you convert these indices to physical quantities? That is range in meters, velocity in meters per second. Those are simple scalings, right? These are the things we had seen before. So from this, to make what is called a range velocity map, what you do is first you take the magnitude of this matrix after the two FFTs, because it's going to be complex valued, but you look at the magnitude of it, and then to go from indices to physical, range in meters, velocity in meters per second, let's zoom in here, you do scaling. So your range becomes like K times FSC over 2MB. I mean, these are the things that we had seen before. Doppler becomes minus L over MT, and then velocity from Doppler is minus Doppler shift times lambda over 2. After you scale your two axes according to these, you end up with, here the visualization is color is basically the value in dB, so it goes from minus 30 to 30 dB, and then the two axes, one is range in meters, one is velocity in meters per second. It is called a range velocity map, but note, it's not the map that we intend. It's just the term used in radar terminology. So it's not map in the sense of, the geometric representation of what the scene looks like, because we haven't done direction of arrival yet. But it's still very useful because it tells you, kind of a lot of information. So looking at this, you can read it as kind of like a heat map, if you will. And where you have peaks in here, like here, that's a target. Right? Everywhere that the values are low, this is just noise. So you ignore that, and then where you have, big values, those are where the targets are. So here, for instance, I can tell that I probably in this scene had a moving target at about, say, 20 meters range and a velocity of about, say, minus 20 meters per second. That's one, because that's a hot spot in my range velocity map. What is this stuff? All of this, it spans a lot of range from very close to far away, but all at zero velocity. So that's all the static parts of the scene, right? I probably had like stuff from very close to me. I don't know where this was captured, but if it was out on the street, maybe it was like, buildings or trees or, anything that's stationary from very close to right about, 120, 130 meters. And those all show at zero velocity slice, basically, in the range velocity map. So that's how far we have gotten so far in terms of the DSP of FMCW radar. We can do range and we can do velocity estimation. One more thing is that the two FFTs, so we did FFT on the rows, FFT on the columns. If you like, you can combine the two and just do a 2D FFT. That's mathematically equivalent. So basically, what you can do is that you can start from your data matrix, raw data matrix, and just do a 2D FFT on it over M and N, and that's equivalent to two separate 1D FFTs. It's just mathematically equivalent, and that directly gives you your Range-Doppler processed, basically, data matrix. And again, remember, R tilde i's, they have peaks where, according to target range, and D tilde i's, they show peaks according to the target velocities. So when you multiply the two, you get peaks at the correct range and velocity of the target. Here's another picture. Again, this is a little more compact. So you start from one frame of data, okay, coming in, and then you accumulate the IF signal into this m by n raw data matrix, and then you can do a m by n 2D FFT on it, and that gives you this SIF of ln k, and then on this, or on the magnitude of this, if you do peak search, that gives you the range and velocities of the targets. Here's another visualization of the range velocity map. Here, instead of like an image view or a heat map view, we're doing a full 3D surface. So same data, it's just visualized differently. But for this one, it shows two pretty, significant peaks. So those correspond to two targets. Looks like in this case, they were both at around 100 meters range, and one had, I don't know, a velocity of like maybe minus 15 meters per second. The other one had a velocity of maybe 30 meters per second or something like that. But the point is, from here, you can detect usually, you can do target detection on this, right? So for instance, if you apply a threshold and just keep everything that is above a fixed threshold, that could give you your targets. That's one way of doing target detection on this. Any questions? Yes.
What does the magnitude mean? Like kind of the signal strength of the IF signal?
Yes, after the FFT. So the magnitude here is basically the norm of this big SIF of ln k.
According to that, because we know the
Or
magnitude
log of it.
targets and then maybe the magnitude of the noise, so can it be transferred into SNR or something like that?
Yes, so if you want to estimate SNR, one way of doing it is that if you look at part of this where you know there's no targets and average that, that can give you kind of like your noise level, right, noise floor, and then you take your targets and then you divide like your target value by the noise floor, and that gives you a measure of SNR. But you have to know, look at, or maybe the previous one is better. If I go here, like over here, if you know there was no target, you can just, average here, and that gives you kind of like your noise level. And then, yeah, use that to estimate SNR. That's one way of doing it. Okay, last thing we need to do is, with this algorithm, what is the velocity resolution and maximum velocity you can detect? Well, it's another FFT, right? So the exact same argument we did for range applies. What is the velocity resolution? It's the width of, one Doppler, one FFT bin for the Doppler FFT. So when it comes to the minimum Doppler shift that we can discriminate, that delta F is the sampling rate on the Doppler axis, which was f prime s, divided by the number of points in the Doppler FFT m. And we know f prime was just 1 over t, 1 over the chirp time. So it becomes 1 over m times t, or 1 over the total frame time. Okay? So if you want better Doppler resolution, you need longer frames, basically, larger TF. In terms of what the exact velocity resolution is, delta V, we know how it's related to delta F. It's delta F times lambda over 2, and then plug 1 over TF for delta F, you get lambda over 2 TF. So to improve your velocity resolution, you need a longer frame duration. Okay? And then what is the maximum velocity you can detect? Maximum velocity also corresponds to the maximum frequency that you can detect in your Doppler FFT. One very important thing is, when we were doing this for range, we said range is always positive. So in the range FFT, we look at frequency 0 all the way to Fs. Velocity can be positive or negative. So when we're looking at your Doppler shift in the FFT, you basically search the FFT from minus Fs prime over 2 to Fs prime over 2. So you basically take it two-sided, and that's why you get this. So the maximum frequency that you can find in your Doppler FFT before it becomes ambiguous is half the sampling rate, because you want to go two-sided, basically. So half the sampling rate, plug that in, and it becomes lambda over 4t. Interestingly, both this and this are the exact same that we got when we first did the simple velocity estimation from just 2 consecutive chirps. Just, I don't know, 20 minutes ago, we got the exact same, velocity, resolution, and maximum velocity. Again, it makes sense because we are doing the same algorithm. We just extended it to m chirps instead of 2. So it kind of makes sense that it doesn't affect the overall resolution or maximum velocity. OK, so here's another trade-off basically for you. If you keep all the parameters constant and just decrease the chirp duration t, what happens is that it will decrease velocity resolution. Right? Why does it decrease velocity resolution? Because if you decrease t, you decrease tf, you decrease tf, your delta VR goes up. So you lose velocity resolution, but you increase maximum velocity, again, because your t goes down, your maximum v goes up. So that's a trade-off between velocity resolution and maximum velocity that you can detect with this algorithm, with the FFT algorithm. Any questions? Yes?
Why in this case do you have to, for the sampling of the Doppler, why is it like quote unquote Nyquist, I guess? Why is it fs over 2 and not just fs?
Well, it is Nyquist, but it is minus fs over 2 to fs because if this is my frequency after the FFT, and that's 0, so Nyquist tells us you have to be, within the sampling rate before things start to, wrap around. So you can pick you have an overall, spectral width that is equal to f prime s. You can pick your starting point, and that determines your endpoint. If you know the quantity or the frequency you're looking for is always positive, you want to start at 0, and then you go all the way to fs prime. But for velocity, we know it can be positive or negative because the target can come towards you or go away from you. So then you make it symmetric. You start at minus f prime s over 2, and then you search all the way to f prime s over 2. And that's why, basically. It's just because it can be positive or negative. OK, so we are kind of like closing this part of the DSP about range and Doppler estimation, or range and velocity estimation. One thing to note is that when we discussed this idea of the chirp waveforms, we assumed ideal chirps. There were these, the chirps that we looked at. It was this perfect frequency ramp, and then instantaneously would like drop to 0, and then you would transmit the next one, and then you would transmit the next one, right? In reality, they don't look like this. There's non-idealities in the waveform. So it's more like this picture here, what a realistic, what you get from actual hardware. So here's just assume like this was the previous chirp. This is the next chirp. And then when you turn off your transmitter, there's, this ugly transition down to 0, which takes some time, and it's, there's some wiggling around it. Also, when you start the ramp, there is a little bit of, non-ideality at the very beginning. There's usually a kink in the frequency. So there's only a part of the full chirp that is, constant slew rate and nice and linear and useful, okay? And that is what the actual hardware uses. So your ADCs are only sampling at the, nicest, most linear part of the chirp, because if they don't do that, all of this, ugliness and distortions will make it into your signal, and your FFTs become very, very noisy, and it becomes very difficult to see what's a real target and what's noise. So that's important to note. Also, there's always some idle time between the previous chirp and the start of the next one. Okay, these are typically small. I mean, it could be a couple microseconds only, but there is some idle time because as you shut down your transmitter, it needs, again, a bit of time for the transients to die off, and then it's ready to do another chirp. That idle time should be factored in when it comes to the sampling rate along the Doppler axis, because we said the sampling rate is just, just the 1 over the chirp duration. But in reality, there's this T effective, which is the chirp duration plus the idle time. So the frequency or the sampling rate on the Doppler axis becomes 1 over the effective chirp time, which is the chirp duration plus the idle time. It's very, very important. And these numbers are known. Like you can go, either you configure it, or it's in the data sheet of the, of the transceiver that you're using. But when you're doing your analysis, just you have to, and your DSP, you have to account your for the idle time for sure. Okay. And last but not least, a lot of these parameters that we talked about, and what parameters did we talk about? in terms of the waveform parameters, things like slew rate, chirp duration, number of chirps per frame, frame duration, carrier frequency. A lot of these modern devices let you configure them. So they can support, a range of each of these variables. So again, this TI transceiver we looked at last time, AWR2243, it's very configurable. And now that we know about these trade-offs, that for instance, you can give up range but get better range resolution, or you can give up maximum velocity, you get better velocity resolution. Now you go and do your study according to your application, and you come up with a desirable choice of these parameters that you can configure your device to use. So you can do studies like this. This has been done for a SISO system, but specifically for this device. In this table, I can tell you which parameters you can configure as the user of the device. So FC, you can configure it, and I think it supports 76 to 81 gigahertz. So you go and specify what center frequency you want. The center frequency determines lambda, because F is just C over lambda. So you set F, and it kind of dictates what lambda is. You can set the slew rate, and then you look at the data sheet. It tells you a range of slew rates that you can do. You can set the idle time. You can set the chirp duration. Slew rate and chirp duration together determines the bandwidth. So that's not a free parameter anymore. You can even set the ADC sampling rate in this device. Again, there's range of acceptable values, but it's user determined. And then once you set the sampling rate, the samples per chip is determined for you. Chips per frame you can also determine. And with all of these set, that also sets your total frame duration for you. And once you have those, these blue ones, so the top ones are kind of like engineering parameters. Those are the ones that you, as the sensor engineer, go and decide based on some studies that you've done. And then from these, you can derive the system level parameters that determine the performance of the system. Things like frame rate, things like maximum range, range resolution, maximum velocity, velocity resolution. So these are the system level performance metrics. So here's, for instance, 3 configurations that somebody has designed for this, and those are for like a long range application, a medium range application, and a short range application. I wouldn't go through the full table, but some things should make sense. So for instance, short range, what is the maximum range? So short range sees up to 62 meters, long range sees up to 250 meters. Okay, so what parameters changed here? So for instance, if you look at the slew rates that were chosen, short range has a higher slew rate, long range has a lower slew rate. Or if you look at, for instance, the ADC sampling rate, you see that short range has a lower sampling rate and the long range has a larger sampling rate. And based on the trade-offs that we discussed, these should make sense because, for instance, how changes in slew rate or sampling rate affect maximum range and range resolution. Anyway, so again, it's not like these numbers are not set in stone. You, as the engineer who is working on an application, should go and design and decide what are the right parameters for your applications. There are some tools that I'm not a big fan of, but I should let you know that exists. So, for instance, TI provides this online tool to design chips for their transceivers. So you go on their website and you decide what device you're using. So these are all the TI millimeter wave transceivers. Go with 2243. You pick up the number of transmit and receiver antennas. Here they're doing it the other way around. So you give them like what parameters you want, like this is the maximum range I want, this is the maximum velocity I want, and so on and so forth. And then it kind of calculates the chirp parameters that you want to give the device in terms of the frequency slope is the slew rate, and the sampling rate, and so on and so forth. And then you can go program the device accordingly. I'm not a fan of this because this sort of becomes a bit black boxy and it hides the low-level trade-offs that we talked about. Now that you know how all these parameters are related, you should do your own analysis and come up, because again, these are trade-offs, and when it comes to trade-offs, you should decide what's the right trade-offs to make. You shouldn't let some black box algorithm on a TI website that God knows which intern wrote when decide the fate of your application. Any questions? Yes.
When you're talking about the idle time, like T effective, when you talk about range resolution, you need to C by 2, E and B. Do we put T effective then there?
Okay, so T effective, and your question was for range? For range resolution, let me think about that. For range resolution, no, that wouldn't get affected because range resolution goes with ADC. That's fast time, right? Fast time is ADC sampling rate, and that's unaffected. You're just, sampling on yours. Your slow time gets affected by the idle time because that adds to the separation between consecutive chirps. Okay, very good. And then, so that's so far the discussion about, we finished the discussion about range and velocity estimation for FMCW. And we haven't talked about direction of arrival yet. We'll get to that. But before that, I want to very briefly talk about PMCW radar. We're not going to go as much in depth, although the full detail is in the slides. If you're interested, I can read about it. But here's a high-level block diagram of a PMCW radar. Again, remember that the main difference is the waveform, right? So these radars send ranging codes for waveforms. So it can be like a maximum length sequence or an M sequence, exactly like GPS, or other types of codes with good autocorrelation, basically, properties. And then you modulate that with some carrier frequency. You pass it through an amplifier and transmit that. And then on the receive side, again, it's the same physics, right? So you get a attenuated, delayed, and Doppler shifted version of what you sent. Your down conversion here is simpler. You just down convert by the carrier frequency instead of as opposed to down converting by the full waveform that you transmitted like we did in FMCW. So down converter is just simple. It's exactly the same as, again, GPS receiver. Filter it, pass it to the ADC, and you do your range and velocity estimation. So at a very high level, the way the ranging works, I think this picture is a good one to look at. So you transmit a ranging code. M sequences are very common for PMCW radars. And then you receive, so green is what you transmit, call that SFT. And then the IF signal that you receive after that down conversion, if there's no Doppler shift, it's just going to be a delayed and attenuated version of your transmitter. And then as we know from GPS, if you correlate the two, that correlation is going to have a peak at an index that is proportional to the round trip time of flight delay, and you can then convert the tau to range, right? So R is basically tau over 2c. Okay, sorry, tau c over 2. Did I get this right? I think so. Yeah. So that's super high level how the PMCW radar works. Now, as I said, today it's not as widely deployed as FMCW. Actually, you cannot go and buy an off-the-shelf, fully integrated, PMCW transceiver, which is kind of sad because it's, in my mind, from an architecture and DSP point of view, it's a more interesting, more capable technology. I hope we'll see more of it. The main reason, if you're interested to know why PMCW is not as deployed as FMCW, is basically this ADC that you need for PMCW. To get comparable performance to FMCW, you need much, much higher sampling rates. And by much, much higher, I mean something like a factor of 1,000 to 10,000 times faster. You need like gigasamples per second or multi-gigasamples per second ADCs for PMCW, as opposed to megahertz or tens of kilohertz per second ADCs or kilosamples per second ADCs for FMCW. And that makes today the PMCW a more expensive device to manufacture because it becomes more power hungry and more expensive to build in silicon. But that's changing. I mean, year over year, we know how silicon technology works. These things get faster, cheaper, better over time. So I think soon we're going to see more and more, ready-to-go, turnkey, off-the-shelf PMCW transceivers. There's none today, so if you were to build one of these, you have to either you have a lot of money and design a full ASIC and do a tape-out, which is fine. If not, you need to build it in the so-called discrete way. So you go and buy a discrete waveform generator, a discrete up converter, a discrete power amplifier, and connect these either on a PCB or with transmission lines. And you can build it, at least with a few antennas. It's very doable, but it becomes very quickly unmanageable if you need big MIMO systems that are PMCW. So that's a limitation, and that's why you're not going to go in as much depth. Although again, full everything is in the slides, but I don't want to spend too much time on it on class. So that's high level how ranging works when there's no Doppler. What about when there's Doppler? Interestingly, the Doppler part of PMCW becomes identical to FMCW. So what you do when it comes to both range and Doppler estimation, you assume that Doppler does not affect your ranging exactly as we did for FMCW. So basically that phase term varies slowly enough that does not affect the output of your correlator. So you just do your correlation as is, but then you accumulate a bunch of code words, and post-correlation you do FFTs on the columns as we did for FMCW, and that FFT basically gives you the full range Doppler map or range velocity map for PMCW. Any questions? Okay, so that basically concludes part 1 of radar. Now we're going to start part 2. So in part 2, we're going to mainly talk about 2 things, radar target detection and direction of arrival estimation. And direction of arrival, and both of these, they don't care, is it PMCW, is it FMCW, they operate on range velocity maps, which is after processing range and Doppler, whether it be PMCW or FMCW. So that part does not matter at all. That's why we don't even make that distinction as we talk. So starting with target detection, what is target detection? Target detection is, if you remember a few minutes ago when we looked at these range velocity maps, in there, it's kind of like you can visualize it either as a heat map or a 3D surface plot. Targets show as strong peaks in there, okay, and everything else is noise. So the target detection basically goes and just tells you where are the targets, and so you only focus on those when it comes to direction of arrival estimation. Okay, so it distinguishes real targets from noise or clutter by looking at the range velocity map. So you can kind of think it's going to be, in the simplest form, it's going to be some thresholding, basically, that you do. Many different ways of doing it. A simplest one is just you apply a fixed global threshold to your range velocity map, and everything that's above a threshold, you declare a target. Everything that's below the threshold, you declare noise. Or you can do a more fancy type thresholding. A very common one is called the CFAR thresholding, or constant false alarm rate thresholding. And overall goal is to have a high true positive rate and keep your false positive as low as possible. So with the fixed thresholding, basically what you do is that, again, if I draw a mini range Doppler map here, so the cells, and let's say you have like range on one axis, Doppler on the other axis. You can decide some fixed threshold, P fixed, and then compare the magnitude value of every cell, basically the absolute value of it, to that P fixed. And if that value is bigger than P fixed, you basically declare a detection. You say target in that cell. And if it's below the threshold, you say, oh, nothing here, that's just noise. Okay, and you do that for the full range Doppler map, and that's how you do your basically detections. Now it's tricky to decide what a good choice for P fix should be, right? Because it depends on, as Shubha brought up, depends on the SNR or the noise characteristics, which in many applications are either unknown or they change over time, okay? But in the cases, if you have, a system where you say, oh, my noise is some Gaussian distributed with mean mu and variance sigma, then sure, you can choose a P fix that is mu, say, plus 3 sigma. And then that, by the Gaussian statistics, just gives you a very low false positive rate of 0.13%. And that's okay. But in practice, it's not that clean. Again, either your noise statistics can be complicated, can be unknown. They're going to change over time with temperature and things like that, or sometimes there's external interferences that are time varying and they raise or lower your noise floor. So that's why fixed thresholding is typically not a good idea except for very well-controlled simple applications, and oftentimes you want to do some adaptive thresholding such as CFAR. So very quickly, we'll look at the math next time, but what CFAR calculates is that, again, for your range velocity map, what it does, the core idea before we do any math is that if you have a target at some cell, these are usually range velocity maps as we show in the previous slides. These are pretty sparse. Like you have a target and then there's nothing around it and then there's another target. It's not very a dense map. So the idea is that if you have a target in one cell, the cells around it are mostly noise. So if you average the value of the cells around the target, that gives you a good idea of the local noise floor where that target is. So you can just compare the value of each cell to the average of the cells around it. And if it's much bigger, then you say that's a target. Because around it, it's just noise. So that's basically the idea. So CFAR basically gives you a per cell. Instead of one global threshold for the entire Range-Doppler map, it calculates a per cell threshold, which is adaptively, adjusted. And then for each cell, if the magnitude of the Range-Doppler value is bigger than the CFAR threshold at that cell, so note that now our threshold is a function of the cell indices. I just noticed an inconsistency in my notation. I think the n should be k because we used k for after the FFT index. So sorry about that. I'll correct that. But this is SIF of L and k. And so each cell is compared to a threshold that is calculated for that cell. If it's larger, you declare target. If not, you say that's just noise. And next time we'll look at how actually CFAR works. Questions? All right, let's quit, and I'll see you next time.